Watch this glass shatter. The physical impact and the exact sound of the fracture occur at the precise same moment. Current generative AI models struggle to build scenes like this because they rely on sequential pipelines. They either generate the video first and fill in the audio later, or vice versa. This modality-first approach creates a bottleneck. It stops the system from learning the true joint probability distribution of the event, how the sight and sound interact simultaneously. Visual first generation creates a one-way street, unable to inform the audio system about precise environmental acoustics. Flipping the pipeline leaves the audio model guessing, unable to dictate physical impacts or match phonemes to lip movements without visual context. Achieving true audiovisual coherence requires a model designed from the ground up to allow simultaneous, bidirectional influence between sight and sound. That brings us to LTX2. It is an open-source, asymmetric dual-stream diffusion transformer built specifically to model this joint distribution. It accomplishes this joint modeling without forcing video and audio data into a single, compromised, shared latent space. Here is the system's macro architecture. Raw audio, text, and video flow into completely distinct pathways before reaching the transformer. We must analyze three engineering choices: latent decoupling at the inputs, asymmetric capacity in the DIT blocks, and cross-modal attention binding the two streams. LTX2 succeeds because it treats video and audio as vastly different data types that must be governed by a shared, synchronized temporal logic. The first engineering constraint in this system is how to effectively represent and compress both video and audio signals before diffusion begins. Looking at the input stage, the model extracts modality-specific latents using independent VAE encoders. These representations remain entirely separate. This separation is of dimensional necessity. Video intrinsically requires 3D spatio-temporal latents to track motion, while audio strictly requires 1D temporal latents. By utilizing these modality-specific causal VAEs, engineers can independently optimize the compression levels for each signal. This avoids the inefficiencies that arise when forcing both data types into a uniform structure. Once those latents are prepared, they enter the main diffusion transformer backbone, where we see a deliberate asymmetry in the system's design. Notice the parameter capacity assigned to each stream. The video stream utilizes 14 billion parameters, while the audio stream requires only 5 billion. This unequal split directly reflects the disparity in information density. Video possesses vastly higher spatial complexity than an audio waveform. This asymmetric allocation ensures that computational resources are spent exactly where they are needed, preserving visual fidelity without over-parameterizing the acoustic pathway. But separating the streams creates a specific alignment challenge. How do you align a 1D audio sequence with a 3D video sequence during the denoising process without destroying the spatial data? This cross-attention module acts as a bridge, enabling intermodal exchange at every transformer layer. First, independent video and audio states transform into queries, keys, and values through learned linear projections. Then, the model applies temporal 1D rotary positional embeddings, or ROPE. During this cross-modal exchange, the spatial components of the video's positional embeddings are deliberately discarded. The model doesn't attempt to map a sound to a physical coordinate at this stage. Instead, aligning the queries and keys purely along their shared temporal axis enforces strict subframe synchronization between the moving image and the audio waveform. This flowchart illustrates how the model regulates the intensity of that cross-modal exchange based on the current diffusion timestep. It uses cross-modality AdaLN gates. The scaling and shifting parameters for one modality are actually conditioned on the hidden states of the other modality. This architecture allows each stream to dynamically dictate how exposed it is to the other's influence at every single step of the denoising sequence. Temporal binding fails if the generated lip movements don't match the specific semantic phonemes of the spoken text. Complex speech synthesis requires linguistic context far richer than what standard final layer text embeddings can provide. This text understanding pipeline uses a Gemma 3 12B backbone. Instead of a single output layer, a multi-layer feature extractor aggregates data across all decoder layers, capturing a deep linguistic hierarchy, from phonetics to complex semantics. Finally, thinking tokens are appended to the embeddings. These thinking tokens act as global information carriers. They allow the bidirectional text connector to process and refine the context before it reaches the diffusion model. By mathematically enriching the text representation, the diffusion transformer receives the precise phonetic instructions required for expressive, lip-synced speech. This architectural decoupling provides direct control during the final inference stage. To balance these distinct conditioning signals, LTX2 introduces a multimodal extension of classifier-free guidance, or CFG. This chart shows how the final predicted output is shaped by two separate guidance vectors. The text guidance term and the cross-modal guidance term are calculated independently. This bimodal CFG scheme empowers engineers to independently tune semantic accuracy against tight audiovisual synchronization on the fly. Grounding the theory, we see the video-to-audio attention heat maps tracking a car down a street. The brightest spots follow the car, perfectly aligning with amplitude specs on the audio waveform below. The visual space successfully dictates the generated acoustics. The second chart reverses the perspective to show how audio dictates visual motion. Here, the audio-to-video map locks on to the source of the sound, demonstrating the bidirectional nature of the trained system. By decoupling latents, embracing asymmetric capacity, and enforcing 1D temporal cross-attention, LTX2 establishes a highly efficient foundation for true joint audio-visual generation.